Next, let's see operating system programming structure. So at the very beginning, only one program is loaded into the memory and processed by the CPU. So when the program needed to do some I/O, such as read something from the hard disk or write something into the hard disk, and the CPU just wait there and keeps idle, so which wastes the expensive and precious resources. So people think that can we improve the performance and keep the CPU busy? Then the idea of multi-programming has been proposed. It is also called batch system. So the idea is quite simple. Instead of loading one program to the main memory, so we can load a batch of programs in the main memory. So for example, on the main memory, beside the operating system, so we have three programs, P1, P2, and P3. So firstly, CPU process P1, and P1 fully occupies the CPU. So when P1 needs to do some I/O, then P1 will be moved to the device controller. Then CPU is available now. So P2 will be put on the CPU and running there. So the same idea is applied for P3. So when P2 needs to do some I/O, the CPU can be used by P3. So we can see that the CPU keeps running there and the performance of the operating system is highly improved. Another programming structure in this slide is called time sharing, which is also called multitasking. So one thing you guys need to be careful, do not confuse it with the name of multi-programming. Multitasking is extended version of multi-programming. So instead of waiting a program to do some I/O, then move another program into the CPU. So time sharing gives a fixed amount of time, actually it's very short, to every process. So when the time is used up for the current process, so immediately the next process will be moved to the CPU and running there. Due to the very frequent job switches, so each program feels that it is the only program using the CPU. So time sharing is a very good structure to support interactive computing. So nowadays, most of the personal computer which use Windows, Mac OS, or even Linux, actually they are using a time sharing programming structure. Then some students may ask, so looks like the time sharing is always beating multi-programming one. So why we still have a multi-programming structure? So time sharing actually is not perfect due to very frequent job switches to trade-off interactive. So it has to sacrifice some performance because when we switch the job, we have overhead, right? So we need to move the data between CPU and main memory. So during this time, the CPU cannot do anything useful to the user. Although the period of time is very short, but the accumulated overhead actually cannot be ignored. And also compare the time sharing and the multi-programming structures. Time sharing can provide more interaction and the response. So however, since time sharing sacrifice the efficiency a little bit, so if you want to maximize the efficiency, maybe multi-programming is the best choice. So that is why most of the supercomputers still use multi-programming as their programming structure right now. Operating systems do a lot of operations. So some of the operations are pretty standard, such as running some programs for the user, load something from the hard disk or device controller to the memory, or put some old program out of the CPU and put the new program into the CPU. However, sometimes if you are not careful, some operations may endanger the system. So in the previous slide, we have a talk about the interruptions. So there's one type of a software interruption called exception, which can use to handle those kind of errors or problems. So when those errors or problems happen, the exception interruption will be triggered. Then operating system will take control to decide whether needed to terminate the program or not. So in order to protect other programs affected by those errors or problems. The other type of operating system operation is called door mode operation. In this type, there's one bit on the hardware to decide whether the current operation is on user mode or kernel mode. So in the user mode, the user can do very limited operations, which can never damage the system. So for example, you can add some integers together or do some calculations. So beyond that, if user wants to do some other operations which can potentially damage the system, the users, they must send an operation request to the kernel. Then the system mode will switch from user mode to kernel mode. And the kernel mode will further check whether this operation request is harmful to the system or not. So if not, then the kernel will do the operation on the user's behalf and return the result back to the user mode. So otherwise, the kernel will simply terminate the operations and send error message back to the user. So in this slide, it shows us the system call example. So the user initials a system call, which is the formal way for the user program to request a privilege operation from the kernel mode. For example, here, the user wants to write something into the hard disk. Then the system call is required for doing that. So when the kernel receives this privilege operation request, it will first check whether this user has the right to write something into the file or not, such as whether the file belongs to this user, not someone else, or this is not a system file, or this is not a read-only file. So if the answer is yes, the kernel will help the user write the stuff on the specific file. Otherwise, the kernel will return a message to notice the user that you do not have the right to do so. And then some student may ask, for the mechanisms or operations you have mentioned so far, actually I can still damage the systems. And I'm not going to request the privilege operations from the kernel mode. So I just do the standard operations. For example, the addition. So each time I just add one into a base number, and I just keep doing that forever. So which is infinite loop. So keep occupying the CPU, avoid other programs to use the CPU. So for the previous two operations, definitely you can harm the computer and to make the computer stuck there. However, the third operation is right for the situation we just talked about. So the system will set a timer when put a program into the CPU. So when the time is up, the current program is forced to move out from the CPU, and the other program will be put on the CPU and set up another timer for it. So for doing that, the hacking strategy we just mentioned actually can be handled.